Hi everyone and welcome back to Newegg TV. My name is Paul and today we have a very special guest here in our studios. This is Darrin from Intel. How's it going, Darrin?
Good, Paul. How you doing?
I'm doing fantastic. Darrin has brought along some Intel processors, and these are not your old Intel processors. These are new Intel processors.
Brand new. These are the Intel 4th Gen core products, or as it's known out in the world right now, Haswell. This is our new part for the summer.
Excellent. So if you guys have been following along with pre-release stuff, well, Haswell is probably the name you might be familiar with. We've been talking about core products for quite some time. So we had 1st Gen, which was just 1st Gen, so it was just core. 2nd Gen was Sandy Bridge.
Yes.
3rd Gen was Ivy Bridge. We got one of those right here. 4th Gen, Haswell. And let's talk a little bit about Intel's development cycle.
Sure.
You guys have been going with a cadence that is commonly known as tick-tock for quite some time. Could you, for the users at home who might not be familiar with that, how does that actually work?
Tick-tock's pretty simple. What a talk is, we'll start with the talk. A talk is we have a brand new microarchitecture on an established lithography or established manufacturing process.
Okay.
What a tick is we take that established engineering and we move it down to a smaller manufacturing process.
Okay.
So we went from 32 to 22, 22 to 14, 14 on down, right? So when we do that, so these are 22 nanometers, the same as Ivy Bridge was.
Okay.
Ivy Bridge was the tick on the Sandy Bridge talk. So talk Sandy, tick Ivy, talk Haswell.
So talk Haswell, so new architecture,
yes.
But we're still using the 22 nanometer lithography that Ivy Bridge used.
Correct.
And what sort of benefits do you actually get by continually shrinking down that lithography?
It's a very simple benefit. If I can put more stuff into the same size, I can do more features. It's your closet, right? If I make your closet bigger, I can stick more stuff into it. So when we go from a billion transistors to 1.1 billion because we've done a shrink, then I can add those to do all the various things. I can add more features. I could actually keep it at a billion but make them smaller and get more energy efficiencies. I can do a lot of different things by having smaller. And the other big thing that it does for us, which we don't really advertise, but it's mostly for Intel, and it's how we're able to get economies of scale. As we have a wafer this big and we can put smaller and smaller dies on there, we can get more wafers, which gives us economies of scale. Everything is better. We can pump out more. It's better all the way around to go to a smaller manufacturing process.
Okay, and that all goes back to the fabrication process where you're actually designing these. If you guys have ever seen it, it's like a circular thing you might see in some of the Intel
300 millimeters.
300 millimeters?
Yes.
And you can just fit more of them on there. So
just fit more on.
Increased yields.
Yes.
Let's talk a little bit about some of the technology that's actually integrated here. I hear the word tri-gate transistors, 3D transistors thrown around. That was introduced with Ivy Bridge?
With Ivy Bridge, correct.
So what is that, and how does it improve the way that the processors work?
If you look at the way a transistor works, right, we have 2 gates coming in, and then we have an output. When we did 3D transistors or tri-gates, we had 3 inputs coming in. So we were able to take the efficiency of a transistor or take the workload of a transistor and add more to it. We couldn't make the transistors bigger. Obviously, we're shrinking. We reach a point where we can't add more, or as we start to add more, which is, if you look at backing up to another technology where we went to the high-K metal gating, that was where we said we're getting so much leakage across these transistors, we had to put a different kind of metal on there to keep the leakage smaller, or the leakage less. So doing all of those things, the 3D transistors now allow us to pump more information through or to do more work in the same amount of space.
Okay.
If you get down to it, right, a nanometer is about a human hair. Excuse me, 1,000 nanometers is about a human hair. Oh, so we're setting at 22 nanometers here. So you can think of the size of that, and when we put 2 wires very close together, we get leakage back and forth between them, the power leak. So that's why we went to high K, and then the 3D transistors allow us to put 3 of those non-leaky wires together to get an output.
Okay, and not to dwell too much on the actual architecture here, but when we're talking about lithography and 22 nanometer, how narrow that is, these are actually the tiny little channels, almost like little rivers of information within the processor where electrical signals are transmitted.
That's exactly it. We lay it down, then we etch away and build our channels, lay it down, etch away some more and build our channels, and that's how we get the information from point A to point Z, and all points in between is along those little channels, and that's the nanometer size.
Excellent. So an incredibly complex process. Intel is the leader in the industry when it comes to these types of designs. Tri-gate transistors is one of those things that's really been revolutionary as far as the industry goes. But yeah, so that's sort of a little bit of a talk about the difference, well, with this talk Can I?
Yes,
Okay.
the talk with the talk.
The talk with the talk from from Ivy Bridge to Haswell, from 3rd gen to 4th gen. But let's now move on to a little bit about what goes hand in hand with the processors. That would be the motherboards.
Yes.
We have a new socket, so that should be made clear to folks. If you do have a socket 1155 motherboard, these are not going to be backwards compatible with that. But
that's correct.
What sort of benefits do you get by actually going to a new socket? Are there design changes that can be made?
It's LGA 1150,
Okay.
so it's down 5 pins, and it's just, everybody asks all the time, hey, why do you keep changing this? Why do you keep changing this? When you look at the way we design these, we move things around, we may get a better efficiency by, if you look at this one, we've increased the graphics capabilities inside of here, which for 90% of the world, the internal graphics here are more than sufficient. So the way if we make them bigger, we may have to add another power pin. We may have to add some input-output pins. So in doing that, we have to change the way it's laid out, which means we have to change the socket.
Okay.
So we don't change them just to make everybody buy something new. We actually change them for an engineering reason. So what's great about the new motherboard? The new motherboards allow us to do a couple of things. The first one is something we called Fiber, or the fully integrated voltage regulators.
Okay.
That was a fairly significant change. We took a lot of the power management and we put it inside of the processor. We've changed the number of 6 gig SATA ports, or SATA 3.0 if you want to call it that. We know we were a little short on the previous generation, so by going up to 6 on board in our chipset, it allows for great efficiencies. The motherboard manufacturers love it, we love it. Better direct talk. If you have to put a chip down on the board for that, the chip talks to somebody who talks to somebody.
And adds a middleman.
Right, adds a middleman, right? So by putting them on our chipset, we get direct talk. We've also gone up to 6 possible USB 3 ports, so that's great as well. Obviously, we tripled the number of those. So just more ports on our chipset adds efficiencies to everybody. We see speed increases. Everything about it is better if we can get more stuff into our chipset.
Excellent. So this is an MSI motherboard, so we have the Z87 chipset down here. There's also a couple more other chipsets launching.
Yeah, we have a few other chipsets. We have the H87, which is our top-of-the-line, non-overclockable, what we would call a home system, right? So if you were building the system at home for the kids to do the homework and have a system, for the next few years, that's probably where you'd be, is H87. We also have our Q series, which is our business series, of course, 87, 85, and then B85. And then later on, we'll be launching a lower class, or a lower cost chipset down at the H81 series.
Okay, but for most of our viewers, we tend to have, I think, a lot of gamers, a lot of enthusiast power users out there. So Z87 is definitely going to be the way to go. And just to close out on the chipset, you already mentioned SATA 6, which is, I love SSDs, so I love SATA 6.
Yeah.
So you get 6 native ports right there.
Correct.
And you also get the RAID support. You can do RAID 0, RAID 1, RAID 5, and RAID 10 all on there. So you can get 3, 4, 5, 6 SSDs, put them all together for an extremely powerful storage array, which is just awesome. But I just wanted to come back to that because it's a feature. Actually, okay, I'll dwell on this some more. We also have Msata, which is another feature. We've been seeing more and more of these. You can take a tiny little SSD, drop it onto your board. Works great as a caching drive, works great also as a boot drive. You don't have to worry about plugging in your SATA.
Right.
But just another nice feature.
I think they're great. We're seeing them. Obviously, it came out of the mobile world a long time ago. It's really moving into the desktop side, and like you said, for caching, frequently used programs putting there. There's processes you can do called pinning, where you can actually pin applications in there. You can say, whenever I launch game X, I want it to launch off my cache drive versus my hard drive. If you're not running SSDs, obviously the speed increase is tremendous there. We can do a lot of different things with the smart caching, which you and I have talked about in the past. Using the Msata is great. I don't want to say waste a port by having a full SSD in there, but it just allows for some cooler configurations.
Excellent. Yeah, and last time I had an Msata SSD that was SATA 6, I had to get a laptop and install it there in order to get it. But anyway, let's go back to the Fiber, as you called it, fully integrated voltage regulation. So, so if you're familiar with motherboards, usually right up in this area you have your power delivery components, the chokes, caps, and MOSFETs that are designed to feed power to the processor. So especially if you're going to be overclocking, if you have a K-SKU processor, those are typically very important. So when you talk about integrated voltage regulation as part of the CPU, does that mean that these components up here are not doing anything, or how's that actually working?
They're still doing things. What we've really taken away from the motherboard is just the actual delivery of taking the power and sending it into processor.
Okay.
The power's still being cleaned out here, the power's still being looked at out there and made sure it's okay. Plus it's delivering to other places on the motherboard, right? So if your memory voltages, your PCIe voltages, all of those voltages are still coming out of here. Essentially what we've done with Fiverr, fully integrated voltage regulators, is we've said, motherboard, deliver us a very clean power that's bigger than you've ever delivered before. We'll take it into one of our voltage regulators internal to the processor, and then we'll divide it up against on the individual rails. Okay. So send it to cores, send it to the integrated memory controller, send it to the system agent. We'll do all the delivery inside the processor itself versus you sending us each of those signals from the external.
Okay, now a follow-up question to that, I think something that's somewhat tied into it. When we talk about CPUs, and especially Intel's design philosophy of CPUs over the past few years, you guys have been sort of doing a combination of power that we have all come to grow and love, but also power savings. We want to talk about efficiency, because not just for desktop, but also for the mobile market, having a very power efficient processor, it's important. Now, what is the TDP on your desktop fourth generation CPUs?
The TDP on our i5 and i7 parts is still 84 watts. I would say still 95 watts. That's our envelope.
Okay.
So you'll hear that a lot too. Why do we say 95 watt when it says 84 watt TDP? 95 is our design envelope, but 84 watts is the actual TDP power usage of the processor.
And that is how much heat that is generated that needs to be dissipated by your cooling solution?
Yes, and we use all kinds of different metrics to measure that, but on an average workload.
Okay.
Define average, of course, but everybody's different, but that's where it is. That's what it's for. We don't ever expect to exceed 84 if you are not overclocking or changing voltages, currents, anything like that. We do not expect you to ever exceed 84 watts.
Okay. Now, here's where my confusion came a little bit, because from my understanding, 4th gen is more power efficient than 3rd gen. However, if you're looking strictly at TDP, which I know isn't the actual envelope, as you mentioned, but it actually is up. So where does that difference come in when we're talking about a 84 watt TDP versus the 77, I believe, that was with Ivy Bridge?
That's correct. 3rd gen was 77, 4th gen is 84. Why? It's the Fiverr.
Okay.
Right. So what we've done is, if you look at this as a whole and say the processor's on there, everything's running, if you were to just say, here's a 3rd gen with all these parts, and here's a 4th gen with the exact same parts, obviously with a different motherboard because of the chipset change, you would see the overall power envelope go down. Okay. Because we've taken where power used to be on the motherboard and we've moved it into the processor with Fiverr. So we've just changed where things are happening. The beauty of that is by putting the voltage regulators inside the processor, it gives the processor more power control, meaning it can turn down, turn off, bring back up, regulate, whatever, much tighter than we used to be able to do it. It's a great power savings. Obviously, that's huge in the mobile world as we're talking battery life. Everybody wants all-day battery life. It's power savings here as well. You'll see it over the course of a year. Quiet, it can go to sleep quicker, it can go to sleep deeper, all of those kinds of things. We can be honest, right? It's mostly meant for mobile because of battery life, but you'll still see advantages and you still see wins on the desktop side as well.
All right, so even though you might be doing a direct comparison to TDP, which I just find it's a spec that I feel like you see more often. So,
yes, you do.
Even though the number might be higher, your overall system usage is still going to be more efficient because of the power delivery components that are being in the CPU now. So that's kind of where that variance happens.
Yep.
All right.
And we try to explain it just that way, to say, yes, we know it went up, but it also went down here. So we've just kind of moved them around, and we're actually a little lower than we were with 3rd gen overall on a platform basis.
All right, so a bit of clarification
there you go.
For myself, hopefully for you guys as well, if you might have been confused about that.
And one more thing on the motherboard I'll put out there, all the attach mechanisms, even though it's a different socket, all the attach mechanisms for thermals are the same. Okay. So we haven't, invalidated your thermal solutions.
So if I built a custom water cooling loop, or if I went for a high-end 240 millimeter closed loop CPU cooling solution, that'll still drop right in.
That'll drop right in here. We've kept the same attach mechanisms.
All right, so that is very handy.
Yes, it is.
As well.
We change the sockets, but we try to keep as much the same as we can. Okay,
so that's kind of a look at the motherboard. Again, goes hand in hand with the CPUs. So Darrin, next up, I want to talk about a feature of Intel processors. It has always been one of my favorites. That is the ability to overclock.
Yes.
Now we have two CPUs right over here, the 4670K and the 4770K. These, from my understanding thus far, are going to be kind of the flagship CPUs when it comes to the mainstream CPUs that are also overclocking enabled. If you have a K at the end of the processor name, that means it's unlocked. It's available for overclocking, so enthusiasts, those are the ones you guys are going to want to go for. What sort of differences would you say exist when you're talking about overclocking with 4th gen versus overclocking on 3rd gen?
There's two real big differences. Okay. One of them we touched on briefly, which is the power delivery. We've added more functionality in the BIOS to control different power features or different power functions, because we know now within the processor we have the power delivery, so we have to allow for different things in there. The other big change, and for those of you that have been Intel buyers for a long time, we're getting back a little bit to where our roots come from. Okay. We've added back into the K SKUs what we call a coarse B clock. Okay. If you are familiar with our current 3960X, 3970X, 3930K, we have that now. Basically what it is we allow you to go in and change the base clock plus or minus 5%, and that is what we call fine clock. And then we've also put two other settings in there. You can change the base clock up to 1.25 or 1.66. Okay. So what that's going to do essentially is set the base clock to 125 megahertz or 166 megahertz.
Okay, and that's something that with Sandy Bridge with the Enthusiast platform, Socket 2011, which is still alive and well, by the way.
Yes, it is.
That's a feature that was introduced with that. It led to excellent flexibility when it comes to overclocking. So that is now also integrated as part of 4th gen.
And then, of course, from each one of the coarse clock adjustments, you can do plus or minus 5% off of those as well. Okay. So you can't go to, let's say 143, but you can get very close to those with our plus minus 5% and the coarse adjusts. We've seen big scores out there. I'll let everybody Google those themselves, right? We won't talk to those. So we've seen that out there. That's worked great for us. Been running wonderfully. Same overclocking basic functionality as before. One of the things we heard and got feedback from and changed was the base multiplier. We capped that at 63 last time. This time we've moved up the base multiplier to 80. Okay. So it gives you more flexibility there. We've done different things. And the best thing about the coarse B clock, in my opinion, is it allows for different kinds of overclocks, meaning now you can take your multiplier, maybe turn it down to 90 and turn your base clock up, or even turn it down to 85 and turn your base clock up, and that allows you to experiment rather than just saying, I'm going to bump one up and bump the other one up. Actually, sometimes turning one down and turning the other up gives you a better overclock. Okay. And those are kind of neat ways to do it. And one other thing I'd like to point out for the overclocking geeks out there, me being one of them, I know that our graphics generally on a K SKU series are kind of looked at as, well, what do I need them for, right? I'd be just as happy without them. We know that they're not for first-person shooter games, all that kind of stuff. But if you are truly a overclocking geek, it's hard to overclock graphics. Yeah. And it's actually fun to overclock the graphics because it's hard to get them right. There's a lot of different feature sets inside the graphics, and we've changed those multiplier numbers and the whatnot as well. So even if you're not using it, it's fun to go do it just to say, I overclocked them. Right? Nice. And just to try it and run the different benchmarks against it. So I actually had a lot of fun doing the graphics.
Another feaure I like about the updated graphics is that you actually have triple monitor support now.
Oh, yes, we do. I actually use the triple monitor support at my desk. Triple monitor base out of there. The only caveat is, it's not quite a caveat. One of them either has to be DisplayPort or WiDi.
Oh, okay.
We've actually ran triple monitor using WiDi, so we plug in VGA, HDMI, and WiDi.
Oh, very nice.
Which is kind of cool if you were going to, put a monitor out wherever, display purposes. It's kind of neat to be able to do that.
I do like WiDi functionality. So for WiDi, just for folks who aren't familiar with that, you need Intel processor, of course, Intel Wi-Fi card as well.
Yes, Intel Wi-Fi card, and then you need the adapter that goes on the TV.
Okay, so a WiDi compatible TV or an adapter to feed that to the TV. Okay, a brief digression there as well. All right, so coming back to overclocking for just a moment, because I know when it comes to overclocking on different platforms, different CPUs, you might not always be able to sort of take the same approach that you had before. Now, I'm going to quickly give a shout out to Sandy Bridge, because Sandy Bridge was a fantastic overclocking CPU.
Yes, it was.
When it comes to overclocking, my methodology usually is to sort of push the CPU as far as I can go without increasing voltage, and then maybe if you need a little bit more to sort of start playing with that a little bit. But as lithography changes, I know there's certain just physics that comes into play when it comes to heat dispersion. So I guess what I'm trying to get at here is you might not want to go and take a voltage value that you were using with the Sandy Bridge overclock and just drop it into a Haswell, I should say, 2nd gen to 4th gen.
Right.
Would that be accurate?
That would be very accurate.
Okay.
We want to watch the voltages all the way across the board, be it memory, cores, whatever they are. Sandy was, let's use the word flexible,
yes.
right? You could do a lot with Sandy. It was very forgiving. As we go further and further down and we're getting smaller in our lithography, our manufacturing process, we don't have the same forgiveness, we don't have the same flexibility. So you definitely want to start out, as you're saying, you know, start at base and start pushing and see where you go. And then from there, make your minor adjustments. You may find that increasing B clock and decreasing cores may be a different voltage signature than going the other way.
Okay.
Right? So there are different things to look at, and just, as we always say, heat doesn't kill it, voltage does.
Okay. Yeah.
Right? So just be careful with your voltages.
All right. So is there, say a high range that maybe you would suggest people not go past?
I always try to give the guidance of please don't exceed 10%.
Okay.
Right? We always say we have a number for our internal that we do plus or minus because we know that there's always a little bit of give and take in there, but if we can keep it under 10%, I feel fairly safe.
Okay, so if you're not that familiar with overclocking, I would recommend heeding Darrin's advice. Of course, I know we're gonna have enthusiasts who are listening to this right now and saying, I'm gonna
going 50%.
If you've got extreme cooling,
right.
If you're an enthusiast, if you have a lot of experience, have at it by all means. But just some advice for those of you folks out there. Yeah. Let's sort of close off. We got we mentioned we had the 4770K right here. We have the 4670K. We also have a couple different product boxes. You guys might notice this one here being a thinner box. So at least some of these are going to be actually offered as a CPU-only solution without an included heatsink fan?
Right. So we know on the KSQs, a lot of people out there are getting them, they're overclocking them, they're putting on, you know, exotic liquid, exotic air, however you want to do it, and they don't really care about the fan. They're grabbing the fan, they're throwing it away. We actually put a lot of plastic in with it, with the whole clamshell. We put extra cardboard, all kinds of things with the fan. Same with our system integrators who said, hey, we're building, you know, 500 of these a month, 1,000 of these a month. We want the 3-year warranty that we get with a box, but we don't want that fan because we're just throwing them away and we're throwing away all this plastic. So that's why we did the fanless box.
Okay.
So only on the KSQs will there be a fanless box, but if you don't care about the fan, you're going to toss it anyway, hey, you know, go a little bit green and go ahead and get a fanless box. That'll be there.
All right, so in a KSQ that would go hand in hand with it.
Right,
I feel like if you're going to be overclocking anyway, chances are you're going to want to go with a third-party cooling solution. So apart from the fanless option with the KSQs, we also have some CPUs that are launching now, some planned for the future. We won't talk too specifically about those yet, but apart from the 4770K, 4670K, we have some others that are launching in the i5 and i7 realm.
So in the i7 space, we have one other one. That'll be the 4770.
Okay.
And in the i5 space, we have the non-K version, so the 4670. And then we walk down through 3 other ones.
Okay.
So we have a total of 7 4th gen quad cores launching. And then later on in the year, we'll come out with our i3s, we'll roll Pentiums, we'll roll Celerons as we're going throughout the year and into next year. Okay,
so a nice product stack available right at launch. Right. More still to come, so if you guys are looking for low-cost solutions, those are still on the way. And then, of course, we have the entire mobile market, which
yes, we do.
This video isn't quite as much about, but that kind of goes back talking with the efficiency of Haswell, the low power consumption. Right. If you are looking for a high-end laptop or Ultrabook, this is going to be definitely a CPU that you will want to have integrated. The power savings is there. You're going to have a longer battery life. You're also going to have an improved graphics performance.
Yes, and I'll be honest, I have a Ultrabook. I have an Ivy Bridge Ultrabook or 3rd gen Ultrabook. And the 4th gen is going to be so much better with the power savings. The battery life is going to go up. I don't know if I want to get into exponentially, but it's going to increase dramatically. Haswell 4th gen is really where we wanted Ultrabooks to land to start with, right? It's going to be an outstanding product. And even in the just the base mobile space, you know, the thick books, as we'll call them that, if you're doing gaming, if you were doing content creation, that kind of thing on a laptop where you're looking at quad core there, the savings are going to be amazing. It's a great product for both mobile and desktop. I think you'd be happy either way.
Excellent. So if you guys are looking for high-end gaming system right now, plenty of those available. We also have, as mentioned, the i3s in the desktop space still to come, as well as Pentiums.
Pentiums and Celerons.
Looking for a more budget system, that's definitely the way to go. And I think that just about rounds it out. I hope you guys have enjoyed this video, as well as all the extra information we've been bringing you about Intel's new 4th generation core processors, previously known as Haswell. Darrin, thank you very much for coming by today.
Thanks for having me.
Thanks to all you guys for watching. If you'd like to see more videos, of course, check out our Newegg TV YouTube channel. Don't forget to subscribe. Don't forget to like this video, because that really helps us as well. We'll see you all in the next video.